It's on now, by the way, just like, you know.
Yeah.
Yeah.
Okay, so this class is just going to be a review, going over just sort of at a high level all of the topics that we've covered so far. That'll be on the first midterm. And so this is a good time. If you have any questions about a topic, feel free to just shout out in the middle or get my attention, because anything you weren't quite sure about, now's a good time to raise that. And I might not, otherwise it may or may not take me the full time slot to get through all the review. But I'll also mention that as of today, I just posted the assignment solutions for the first 2 assignments. And also I posted a short video, about 24 minutes, doing some practice problems, and that's on YouTube. And those problems were based on the problems of the midterm. So they're not the same, but they're sort of the same rough level of difficulty, the same kinds of concepts. So definitely take a look at that if you're looking for some extra practice. And in general, a good way to prepare for the midterm is to make sure you understand the homework problems especially. And the homework problems and the examples that we did in class. There were 1 or 2 major examples that we spent most of the class on. And so if you're comfortable with the problems on the homework and you're comfortable with the examples, you should be at a good level to answer the midterm problems. And just like on the homeworks, you shouldn't worry about anything excessively mathematically tricky on the test. The sort of idea is to evaluate understanding of physics and fluids and that kind of thing, not so much doing complicated integrals or whatever. So I'll just, I'm basically just going to jump into the review and just go topic by topic and mention sort of what we talked about just in a high level way. And then if we get through all that, I'll talk about the problems on the homeworks, what are the sort of things to emphasize, and then what from the practice problems that you guys probably haven't seen, I just posted them this afternoon, but what are the key things to focus on there. But I'll just pause. Does anyone have any questions? I'll also, and the first thing I'll do is go over the structure of the midterm. So does anyone have any questions before we get started? Okay, good. All right. So the midterm structure. So there will be, so it's a full class period, which is 1 hour and 15 minutes. So if you can try to show up on time or a few minutes early, that'd be great, because you're going to make sure you have the full amount of time to do the test. Although it should not take you the full amount of time. So I usually make a test so that it should be able to be done in about 45 minutes. You should, in principle, have like an extra half hour at the end to check things over. But every course is going to be different. So, but I try to avoid the test being excessively long. So there's going to be 4 questions. These could be multi-part, each on a different topic. And these, sorry, I was going to say I lost my train of thought. And so these will include things like sketching, for example. We talked about multiple assignment problems, so sketching flows, kinematic equations, very likely to show up. Material derivative, and main other concepts. So for example, concept of a parcel. Etc. These will be a mix of sketching or interpreting a flow, explanation. So might get asked a short written question, like explain something about pressure or explain the meaning of some concept. And then analytical calculations. And these would be similar to the homeworks. And I'll say, I'll suggest you can bring your calculator, although that's mostly just in case. I think, I'm not sure if there's going to be any numerical calculations, but there might be. For example, if there's an Euler's method question, then you might have do some numerical calculations. Okay, and there'll be a formula sheet. Provided, and I'm going to try to post that tomorrow, so you can know what kind of formula sheet you'll have going in. But in general, you will not have to remember any formulas of any kind. Basic things like integrating polynomials, taking derivatives, like chain rule, stuff from calculus, you're expected to know that. But I'll give you the formula for the gradient operator. I'll give you the material derivative formula, give you the kinematic equation. So those formulas will be given, but you may need to take those and simplify them for a given case. So for example, if I give you the material derivative in all three dimensions, u, v, and w, but you're working on a one-dimensional example on the test, then you'd have to know, like, to drop the v and the w and just do it. So I think that about covers it for the structure of the midterm. Is there anything I left out, or does anyone have any residual questions about how the midterm is going to be formatted? Okay. All right. Oh, and I'll say, so what we cover, so the content included is up to and including the pressure gradient force. And we're not including the Euler momentum equation. At the end of the last actual lecture, right at the very end, we took the pressure gradient force and we put it into F equals ma, and we got this equation called the Euler equation, but we really haven't explored that fully, so I'm not going to put that on the test. What we did talk about, the last real topic we talked about was pressure, like what's the thermodynamic definition of pressure, like microscopic interpretation, and then what is the force that results when you don't have a uniform pressure field, the pressure gradient force, and so that's the cutoff point. So the last bit of the last class we're not going to include because we didn't fully cover that. Okay. So review topics. And this is going to be a pretty high level, so if you have any questions or there anything you weren't sure about, or you want any clarification on anything, just get my attention. We can definitely talk about that. Okay, so we started off with vectors, dot product, magnitude, etc. And so basic things about vectors, how to manipulate vectors, components, all that. It's going to sort of be probably won't be explicit questions about that. There won't be explicit questions that are only math. The math will come in through the physics questions, but that'll be, you'll have to know that to do the problems. Single, variable, and partial derivatives. Have to know how to take those. Taylor series. So this is a big one. So we did Taylor series in 1, 2, 3, or 3 plus 1, meaning 3 space x, y, z, and 1 time t dimensions. And so we can recall that we had in 1D, we had the very simple formula f of x naught plus delta x equals f of x naught plus delta x times df dx evaluated x naught plus an error term that we always ignore. And in 3D, or in 3D plus 1, we had f of x naught plus delta x vector, and t naught plus delta t is equal to f of x naught t naught plus delta t partial f partial t plus delta x dot gradient f evaluated at x naught t naught plus 4 delta squared. And so, so again, so this formula, the actual formula that I just wrote on the board, that'll be on the formula sheet. But knowing where this comes from, knowing how to use it in different cases, we use this on the assignment 1. We evaluate the error. So I would say mostly just understanding where this comes from, not the proof or anything, but just the interpretation. We interpreted this. We interpreted the Taylor series as the Taylor series is the line that matches the value and slope of a given function at the point x naught. And that's in 1D. And in 4D, it's the same basic interpretation. We're just sort of modeling locally a function with a linear function. Okay. So we use the gradient there. So coming from partial derivatives and vectors, we talked about the gradient. So our gradient operator was the vector of partial derivatives. And on the first assignment, you did some just direct calculations with the gradient, calculating gradients of known functions. And then we had the interpretation, which the gradient is orthogonal to contour lines. And also is points in the direction of sharpest increase of a function. And we connected that to ideas like if you're doing machine learning, the gradient descent is a way to sort of find where the function, how can we move in space so that the function is increasing or decreasing rapidly. So this is the mathematical definition, and again, that will be given, but understanding what this interpretation is and how to do calculations with it if you were given a function is what you need to know. This says interpretation. Taylor series is the line that matches the value and slope of a given function at the point x naught, just in case my writing is not crystal clear. Okay, we also talked about differential equations. And our one big example that we used was f equals ma, and a being the second derivative of position. So we have d squared x dt squared equals 1 over m f. And so the concept is to solve the differential equation to provide predictions for future evolution. Of, for example, weather. And we need initial conditions. So the idea is, the concept is that what's the point of a differential equation, other than being something that you have to do in a math course? The point is, if you want to predict the future of something like the weather or the stock market or the trajectory of a baseball, you want to solve this equation. And if you can solve it, then that function that you get is a prediction for what the future behavior is going to be. So if you want to predict the weather, you solve a certain differential equation. If you want to predict the motion of a baseball, you solve a different differential equation. But they all have the same property, that you need both the equation itself and you need the initial conditions. You need to know something about the current state of the system to be able to predict into the future. So then we talked about equations with no analytical solution, and that led us to numerical solutions. Which is based on the concept of discretization. So we take our time axis and we break it up into lots of little tiny blocks, each of which is of size delta t. And then we get Euler's method from that. We essentially approximate the derivative in a differential equation based on this discretization, and that gives us an algorithm that we can use to step forward the solution one step at a time to do our prediction, even in cases where it appears, based on what you learn in differential equations courses, that there's no analytical solution. So there's no pencil and paper closed form formula, but we can still solve it on the computer by discretizing our time and then basically stepping forward this algorithm. And so I'm not going to write it on the board, but the Euler's method formula will be given on the formula sheet as well. But understanding what that formula means and how to use it is something you would have to know. Okay. And something that I could for sure say will be on there somewhere is dimensional analysis. So I think on the first two homeworks, both of them had some small problem on dimensional analysis. So this is where we say the units of force are the units of, or the dimensions of mass times acceleration, which are the product of the dimensions of mass times acceleration, which would be dimensions of mass times dimensions of length per time squared. So the dimensions of force are mass, length over time squared. And so the general idea is all terms in an equation must have the same dimensions. And you can use this to determine the dimensions of a constant. So if you have some quantity in your equation, and it's not obvious right away what the dimensions of that are, you can compare the dimensions of that quantity to the other terms in the equation, and then that can allow you to deduce what the dimensions of that parameter are. And so undoubtedly you'll get some kind of question where you're asking you this. Probably not worth a lot of marks, but just as a check that you understand that concept. Okay, so that's the math review. And so all of that math review, much of that, these concepts, most of these concepts are going to show up in some way, but they won't be explicitly asked like do this with the Taylor series or whatever. It'll be something about physics, you have to use that. Okay. So, now into fluid concepts. So we have the concept of a velocity field. U of x, y, z, t, and this assigns a flow velocity vector to each point, x, y, z, and time at each time t. And so I usually think of this conceptually as a bunch of arrows that exist in space. And so if it's a two-dimensional vector field where you just have u of x and y, it's pretty easy to plot it just as a sort of vectors like you did on the first couple assignments. But just having this concept that how we describe a flow, probably the most important mathematical object that describes a fluid flow is the velocity field. So how is it moving at every point in space? And our u of x and t is really a vector. That's the three components: little u of x and t, little v of x and t, and little w of x and t. Yeah. So that brings us to the concept of a Lagrangian parcel. We also call that a material parcel. And so that is a little cube that is a little cube of fluid that moves with the flow. And mathematically, what that means is if xp is the position of that parcel, then xp changes according to the differential equation dxp dt is equal to u of xp of t and t. And this very important equation, we call it the kinematic equation. And these Lagrangian parcels, or material parcels, were very important because we use them to derive things about the laws of fluid mechanics. So just at the last stage of the lectures, we used it to derive the formula for the pressure gradient force by thinking about the various pressure forces that are acting on one of these Lagrangian parcels. We also used Lagrangian parcel concept to understand how accelerations work in the flow. We tracked how the velocity of a parcel changes, and that gives us the acceleration formula. So understanding that what a Lagrangian parcel is something that moves with the flow, and its position obeys the kinematic equation. And something that's crucial here is that this is the function u, and we evaluate the function. We normally evaluate it at x, y, z, t position and time. But now we imagine we have a particular parcel that's moving through space, and we evaluate the velocity field at the position of that moving parcel and the time in question. And so this is the equation that governs how the position of the parcel changes over time as it moves with the velocity field. And so on some of the homeworks, for example, you were asked to solve this equation explicitly. You can use this to calculate the future positions of the parcels if you're given an initial condition. You say the parcel starts at some position. You can use this equation if you can solve it, just like we solved any differential equation, subject to both the equation and the initial conditions. Then you can track the trajectory of the parcel, and that often gives a lot of insight about how the fluid flow is operating. Okay. So then we talked about parcel accelerations. So acceleration of Lagrangian parcels, and we derived the formula that the acceleration of a parcel is equal to du dt plus u dot grad u evaluated at the position of the parcel. And so what this tells us, very important, is that if you have a parcel that is embedded in some flow, so you have a velocity field, and then there's a Lagrangian parcel in that velocity field moving around, then that parcel, as it moves, will feel an acceleration from sort of two different kinds of origins. So there's two different terms in this acceleration. One is the partial time derivative, And what that's measuring is, if as we were looking at the flow, we just saw it was accelerating. So we're just like looking at a particular point, and at that point it's going faster and faster and faster. Then whatever parcels are at that point will also be going faster, their speed will increase. And so when you increase speed, that's an acceleration. And so you get an acceleration if the background flow is just explicitly dependent on time, it has a partial time derivative, it's either speeding up or slowing down, then that will cause an acceleration. And then the more subtle aspect is this second term, which involves this operator u dot the gradient, so it's the velocity field dotted into the gradient operator. And so this is basically a combination of derivatives, and this operates on the velocity field itself. The key idea here is that we have a gradient that's operating on the velocity field. So these are spatial derivatives operated on the velocity field. So if the velocity field is not constant in space, and so we use the example, if we have a river that's narrowing, and let's say there's a waterfall down here, and the river is coming in like this, and if we look at what's happening on the center line, do this sort of, we think of it sort of symmetrical. As we go down, the river gets faster and faster towards the falls. And so even though, if we look from a top-down perspective, none of these velocity vectors are actually changing, if you have a parcel embedded in here, as it goes down this center line, it moves into the region where the river's getting faster and faster and faster, and so this thing starts to speed up, and it has a positive acceleration as it goes towards the falls. And so that physics of a spatial gradient in the flow generating parcel accelerations, that's encoded by this second term. So the first term is explicit speeding up or slowing down of the overall flow, and the second one is if you have spatial variations in the flow and the parcels are moving through those spatial variations, then they can accelerate based on that. Another way of thinking about this is you can kind of think of it as, if you've ever been in an airport, you know they have those automated sidewalks, you can go faster. So if you look at the automated sidewalk and look at the place before the sidewalk, nothing's changing, right? The sidewalk is moving at a constant speed, and then the flat ground is not moving at all. But then when you move from the flat ground to the conveyor belt, the walkway, you speed up, right? So when you step onto it, you speed up, and that's because you've moved across a spatial gradient to where the floor is not moving to where it is moving. So that's like your derivative of your velocity field. As you move into the region where the flow is going faster, you feel an acceleration. Okay. So this is for parcels, and in general, the acceleration field anywhere is we just drop the p, and we say a of x and t is equal to partial by partial plus u dot grad of u. And so this is the acceleration of whatever parcel passes through that point, so passes through x at time t, is given by this same formula. And that motivated us to look at the material derivative. Which is a very important symbol. We define capital D by dt. It's just defined as the combination of derivatives that's involved in the partial acceleration. We can expand that out to include three different partial derivative terms from the gradient part. So we have our material derivative operator has two terms in this sort of vector notation, partial by partial t plus u dot grad. U dot grad can be expanded out into the three components, u d by dx, v d by dy, and w d by dz. And if you didn't happen to have all three components, for example, if the flow was only in 2D, then you would get rid of this w d by dz term. If it was only in 1D, you could get rid of the v and w terms, and you would just have these first two terms. And sometimes you may be given a fluid flow, like given a formula for the velocity field, in which case you replace these UVWs with whatever formula you're given for that. Those are the values of those velocities. Okay. So we interpreted the material derivative. So the interpretation was that d by dt of anything, let's say it's salinity, is equal to the rate of change of a parcel's salinity as it moves. So you imagine you're following this parcel and you're looking, does the saltiness of that parcel change as it moves? And sometimes it might and sometimes it might not. But ds dt will always measure that rate of change. And similarly, if you had dt dt, temperature, that would be rate of change of T, temperature, following a parcel, etc. So whatever quantity you might be interested in, temperature, salinity, dissolved carbon dioxide, whatever you may be interested in, d by dt of that quantity measures how that quantity changes as you follow a parcel's trajectory. So understanding that interpretation is important. And that brings us to the idea of material conservation. So if we have, for example, the equation capital D S dt equals 0. So if this is true, so this may or may not be a correct equation, depends on the physical scenario, but if it is true, then what this means is that parcels move around, but keep their same salt values as they move. And so very importantly, if ds dt equals 0, it could be temperature, it could be dt equals 0, it could be d carbon dioxide dt equals 0. Whatever we have of the material derivative of that thing equals 0, what that means is that parcels move and they keep their value of whatever that is. So they keep their same concentration of carbon dioxide, their same temperature, etc. But those parcels are still moving around. So from a top-down view, you might still see the surface temperature or the surface salinity or whatever changing a lot. But each little parcel is maintaining its own salinity. But the pattern of salinity changes because those parcels are all moving relative to one another. So this is different. So this does not mean, it does not imply that partial S partial T equals 0. So these are very different statements. This would mean that the salinity field is constant in time, has no time dependence. This means that parcels conserve their salinity. Okay. All right, and so when we discussed those parts of the course, so all those concepts, we did two main examples, both of which took a decent part of a class. And so it could be good to, as part of your preparation, go back over and make sure you understand those examples. So we did two big examples. So one was the straining flow. So this is the one-dimensional flow where we had u of x, which is equal to lambda x. And so in this case, what we did was we solved the kinematic equation. So our kinematic equation was dxp dt equals lambda xp, and that gave us xp of t equals x naught e to the lambda t. This happened to be a separable equation, so again, you would only get simple differential equations. But you could very well be expected to solve something at this level, or maybe a little bit more complicated. And then we calculated partial acceleration two ways. One, direct differentiation. And two, using the material derivative. And these were consistent. So this was a very, really important example because it showed how the material derivative viewpoint and the parcel viewpoint are really, at least you derive one from the other and they're totally connected. So you get the same answer however you choose to do the problem. And our second example was salinity in a uniform flow. And we considered the equation, our 1D flow, u of x is just equal to u naught equals constant. So our flow just looks like this. Constant flow. Up here, our flow looked like this, getting faster and faster as you move to the right. This one just constant. And we looked at the equation ds dt equals 0. So salinity is conserved on parcels. And we said we know the initial distribution of salinity was some known function. And we broke this down in one dimension as ds dt plus u naught ds dx equals 0. And then between the in-class example and on the homework, we showed that the solution here, do you have a question?
What does it say, salinity?
Salinity is conserved on parcels.
Okay.
Yeah, so we had the solution, s of x and t equals s naught times the exponential of minus x minus u naught t squared over L squared. And between the in-class example and on the homework, we first of all showed by direct differentiation that this solution solves this differential equation by calculating the two terms, ds dt and u naught times ds dx, and showing that they cancel, they're equal and opposite. So this solves the equation. And we also showed on the homework some neat stuff, which is that this equation here, it implies, so if each little parcel of water is conserving the amount of salt it has, keeping it constant, but these parcels are just all moving around, then you would think, well, the total amount of salt in the system is the sum of the salt in each parcel, and they're all staying the same, so the total amount of salt should be conserved. So we showed on the assignment that this equation actually implies that the total salt, St, defined as the integral of S dx, is equal to a constant. So just understanding that concept is good to know for sure. And on the assignment, you did show this two ways. First, proving it from the equation, and second, just explicitly evaluating the integral and showing that it equals constant. Okay. So all of that, we talked about math first, and then we talked about fluid concepts like Lagrangian particles and vector fields and velocity fields and accelerations. But all of that was basically assuming that we knew what the flow was. So we were given the velocity field, or we were analyzing a velocity field in general. That was sort of kinematics. And then, whereas dynamics is what creates the velocity fields, forces. Dynamics really means forces and the interplay of forces. For dynamics, we talked about what forces are involved in fluid flow. And there are a few that we're going to discuss, but we really so far have just focused on the pressure force. And so we talked about how the pressure is defined as the pressure force divided by the area, so pressure is a force per unit area. We also said that pressure is not necessarily the same everywhere. We know that it's high in the deep ocean, that's why it smushes those styrofoam cups, and it's low on mountaintops, which is why it's you need oxygen tanks and things like that. So pressure is a field. Depends on space and time. We said pressure squeezes submerged objects. And so we have some box, for example, then there are pressure forces acting on all 6 sides of this cube. I go through a simple example, a simple explanation question in the practice questions about how do you know that if the pressure actually turns out to be uniform? So if pressure is actually a constant everywhere, it doesn't depend on x, y, z, or t, then all of these 6 forces will be equal. So even though the cube is being squeezed on all sides, there won't be a net force. And so the parcel will stay where it is. It won't drift in any direction, but it will be squeezed on all sides. And then we discussed how non-uniform pressure produces a net force. And so the idea here was, imagine we have high pressure on this side and low pressure on this side. So there's a pressure force acting on both sides of the box, but the arrow on the low side will be a shorter arrow because the force here is equal to the pressure times the area, but we'll have a smaller arrow, whereas on the high pressure side we'll have a larger arrow because force, again, is going to equal pressure times area. If you have a higher pressure, you have a higher force. And so this kind of configuration, we have low on the left and high on the right, there'll be a net force pointed to the left, F net pressure. That comes about because the pressure on the right-hand side outcompetes the pressure on the left-hand side, and so it's sort of pushing it over towards the left-hand side. And we work out the formula, and the force is equal to minus the gradient of the pressure. We call this the pressure gradient force. So understanding what force is going to happen between high and low pressure regions, and this idea that constant pressure has squeezing effect but doesn't have net force, pressure is force over area, these basic things about sort of pressure from a sort of mechanical point of view. But then we also talked about pressure from a microscopic point of view. So from a microscopic point of view, we said that you have some fluid. It's made up of fluid molecules. They're all moving around randomly, and then sometimes one of them bangs off the wall, and by sometimes it is happening constantly. There's lots and lots of collisions between these individual fluid molecules with the wall. And so we have force, the pressure force, is due to collisions of fluid molecules with surfaces. And this can be a real surface, like if you put an actual solid cube into the ocean, or it could be sort of an imaginary surface, like if we imagine that we have a parcel, which really is delineated by kind of imaginary boundaries. You can imagine coloring all the molecules in a particular parcel red. But the side of that red cube is still going to get squeezed by random collisions from the neighboring molecules. And so it can either be a real boundary or it can be sort of imaginary boundary. In either case, there's a force, there's a squeezing force exerted on any submerged surface that's proportional to the pressure and proportional to the area of that surface. So pressure is connected to other thermodynamic properties, such as density, which we denote by the Greek letter rho, and temperature, which we denote by T. If the fluid is an ideal gas, rather than seawater, then they're connected through the ideal gas law. P equals rho RT. It's the ideal gas law. And for seawater, this, and I'll say one more thing, is that this ideal gas law is the simplest example of an equation of state, which we sometimes call EOS. And an equation of state is just some mathematical relation that relates the various thermodynamic, thermal properties of the fluid. So the ideal gas law relates the pressure to the density and the temperature, so it's an equation of state for an ideal gas. For seawater, similar relationships hold. But there is no simple formula. So we just usually write that the pressure is equal to some function of the density, the temperature, and the slipping. And then this is really a computer program. And in some simplified situations, you might be able to approximate that with some approximate formula, but in general, the internal physics of liquid water, especially with salt ions in it, is so complicated that there's no real hope of having a simple formula like the ideal gas law, but you can do like a spreadsheet that will, so if you give it the three variables, it can give you the other one. And so for practical oceanographic modeling, there's a standardized equation of state that everybody uses for quantitative ocean modeling. And later on in this course, we'll have to look into exactly what this looks like, and we'll do a simplified version to allow us to study some things like sound waves in water. Okay. All right. So that is actually all the topics I think that we covered. And so what I can do just for the last 20 minutes is go through the homeworks a little bit. So I can just bring them up on the screen here and highlight what are some of the main skills and what are the main questions to make sure you go over on the two homeworks and on the practice problems. But now that I've gone over all the concepts, I'll just pause for a minute. Does anyone have any question or anything that was, hard to understand when we covered the first time that they want to ask about now that we've reviewed the topics? Yes?
What does IGL mean again?
IGL stands, I should have wrote that, yeah, it means ideal gas law.
Oh, right, okay, thank you.
Okay, anything else? All right, so I'm just going to give a minute to copy down what's on the board, and then I'll just bring up the screen and just go through the problems on the homeworks and maybe show some of the solutions. Not in a lot of detail, but just highlighting which ones you should really make sure you know the mechanics of the solutions. Does anyone need another minute to copy anything down? Okay, so this was the first homework. So the first problem, definitely this is a good one to go over because I think, as I mentioned in the outline or the structure of the test, some kind of visualizing a fluid flow of some sort is definitely going to be on there, so you're going to have to make some kind of sketches. So the first bit was sort of interpreting what this means. So this is a velocity field. This tells you the x component of the velocity field and the y component of the velocity field in terms of explicit functions of position in the xy plane. And then there's this parameter in here to make sure the units are good. So if you're given a question like this on the test, you can figure out what the units of A are by noting that the left-hand side, the velocity has to be length per time, and then you know x and y are both length. So by plugging in those two things, you can solve for the dimensions of A. Generally, when you're asked to sketch a vector field, what you want to do is pick some points usually around the origin, and usually it's some kind of circle or square or some points around the origin, and just start drawing what the vectors look like. Once you have a lot more experience, it'll start to become kind of like a little bit more, I don't want to say the word obvious, but it'll be easier to sort of guess what the flow will look like just based on looking at the formula. But for the first few that you see, it's harder, and so just graphing some of the vectors is a really good way to do it. So in this case, I suggested 8 points. You just draw your arrows, and that gives a picture of what the vortex or what the flow looks like, which in this case is a rotational vortex. And then the last part was just compute some partial derivatives, something something like this probably wouldn't be on there, just straight differentiation. Gradients is just straight math, so you won't get a question like that. Euler method. So Euler's method could definitely be on there, especially if it was applied to a differential equation that comes from fluids. And so this was about doing the problem 2 ways. So you're given a simple differential equation. In this case, this one is exponential decay, so you can solve it exactly. It's separable. If you divide by n, you get dn over n equals minus lambda dt. You can integrate that to get an exponentially decaying function. And then the second part is do the first few steps of Euler's method, which is grinding through the Euler algorithm to predict step by step, and you wouldn't have to do more than 1 or 2 steps on the test, since it's a little bit time consuming. But this is a good reason to bring your calculator, because you might have to do some numerical calculations. And then the last one is more of a numerical problem. So this one, you should really be comfortable with the first step. So given a flow, just apply Taylor's formula to derive an approximation. But the second part about like coding and comparing the errors, there'll be no write a code or anything like that on the test. It'll all be just analytical math and explanations and sketching. So don't worry so much about anything that involves Python, but do know Taylor's theorem, be familiar with that, and dimensional analysis and sketching, very, very important. Okay, that was the first assignment. Second assignment. So again, we have a dimensional analysis question. And in this case, is solving the kinetic equation. So the kinetic equation, in this case, is a 2-dimensional equation because we're given a 2D flow. We have a u component and a v component. And so we're going to be thinking about movement in both x and y. And so your kinematic equation is that your rate of change of your partial position is just given by the velocity field evaluated at the position of the particle. And in this case, you end up getting the equation for a simple harmonic oscillator. and you can combine the equations. And so you get solutions that look like sines and cosines. And it turns out that ends up being the equation of a circle. So the specific tricks that happen that it's a circle and proving that it's a circle might be a little bit more trick-based than something I would ask. But definitely knowing how to write down the kinematic equation, how to solve it, and then how to interpret what that trajectory looks like, describe it. Like, is it accelerating, which direction is it moving, that kind of stuff would be important. Yes?
So in this case, we were able to combine like x dot p and
Yes.
y dot p. So I guess what would it look like if we were multiplying? Like we would just have it two separate and then we would differentiate separately?
Yeah, so so in general, if you're given if it's a two-dimensional system, you'll have two kinematic equations, one for the x position and one for the y position, but they could depend on each other. So the x velocity could depend on y, and the y velocity could depend on x.
Okay.
So in general, if you were given like a random flow, it wouldn't necessarily be exactly solvable.
Okay.
So two kinds that are common are something where where the right-hand sides are all constants and you can sort of differentiate one and stuff it into the other one. So that's what you got in the first one. Another kind that can come up that's also easy to solve is if the two equations are not coupled to one another. So if the x one only depends on x and the y one only depends on y, then you can solve them separately.
Okay.
And so that might be another class. But in general, if there's any kind of fancy trick that allows you to solve it in a special case, I'll give a hint as to what the trick is.
Okay.
But yeah, that example is special. So if you got an arbitrary flow, you wouldn't be able to do that trick.
Okay.
And in general, it's hard to solve the equations.
Okay. Cool. Thank you.
Okay, acceleration vector. So acceleration is very important. So once you have the trajectories, you have an explicit function x of t, y of t. So you can calculate the acceleration components just by taking two derivatives. The acceleration is the second derivative of the position. So here we did this two ways. Calculate the acceleration by differentiating explicitly. This is just like the straining flow, except for this was in 2 dimensions. And then we calculated it using the material derivative. And you should always get answers that are consistent, but sometimes to make them look consistent, you have to, at the last step, plug your trajectory back in. So to get the exact same formulas in the end, when you take the material derivative, you'll just get an answer in terms of x and y. It won't look like xp, y sub p. So what you have to do is you take your trajectory results, and this is all in the solutions, from the trajectory part and plug them into your acceleration field, and that'll give a formula that should be exactly the same between part E and part F here. The key part is you can do it two different ways. It's the material derivative version and the explicit differentiation version should give the same answer. Speed of the parcel turns out to be constant in this case. It's just the sum of the squares of the two components is equal to that's defined as the magnitude of the speed. And so in this case, it's constant because it's uniform circular motion. And subtle sort of interpretation stuff like this, probably I wouldn't put on the midterm, but doing the calculation certainly is something that's at the level of difficulty that could be on the exam. And then the second question was the salinity in the uniform flow example. And so here are a couple of the key points are, so going from here to here. So you should definitely understand how to do this. So starting from, if I just give you this formula, and I say the flow is u is equal to u naught equals constant, you just expand out your d by dt into your partial time derivative part, plus your u dot grad part, plug in the explicit velocity field, and you should be able to derive this. So this is the kind of thing that should be 1 or 2 lines. You should be able to do it pretty quickly. So if that's foggy at all, definitely go back over that. If you have any questions, send me on. And then these last 2 bits were sort of theoretical, definitely more assignment questions. These were sort of a little bit more mathematically intricate and sort of thinkers a little bit. But yeah, so this concept that if you have material conservation of salinity, or anything, whether it's carbon dioxide dissolved or temperature or whatever, if each parcel keeps its same value of that substance, so salt for example, then the total amount of salt in the system should be conserved, should be constant. So we define the total amount of salt as the integral over the concentration over the whole space. And in this case, you can work out given a known solution, you can calculate that integral. and show that it's that has a constant amount of salt, even though the time evolves, but the amount of salt is constant. You can also show that directly from the equation. So by basically differentiating this integral and plugging in the advection equation, you can show that the total amount of salt doesn't change. Again, this question is pretty theoretical. So I would say understanding the concept that conservation on parcels leads to a global conservation of total amount. That concept is important to know. The idea that this integral should make sense to you, that the total amount of salt is an integral over the concentration times the integral of the concentration over the space. But theoretical questions like this are probably not going to be of the type that are on the exam. But still understanding the concepts is valuable. But something that you might get more is showing by direct differentiation that this expression solves the advection equation. So in class, what we did was we wrote down the advection equation, which was this one here, dx dt equals u naught times ds dx equals 0. And we just sort of argued physically for what the solution should be like. Whereas in this problem, you're actually taking the two partial derivatives, adding them up, and making sure that it cancels out and gives 0. And so that's a skill that definitely could be tested. And so knowing how to check the candidate solution either is or isn't a solution to a differential equation, that's valuable. Okay, and so that's the two assignments, and now I'll bring up the practice problems that were just posted today. So I know you guys haven't had a chance to look at these, but there's a video of me walking through. I did screw something up in the middle and had to like stop and go back a little bit, so sorry about that. But if you get to that point, you just wait 30 seconds, I get through it. So this first problem, so I put 4 problems up. So the first 3 are sort of calculations that are of the level of difficulty that could be on the exam. And then the last one is an explanation question. So the first one is about material derivative and like working with the formula for the material derivative. And the question is, use the definition of the material derivative to show that for any random function, that if you take the derivative, the material derivative of the function squared, so d by dt of f squared, that equals 2 times f times the df dt. And so if this was regular d by dt, not capital D, then this would just be the chain rule. But in this case, we're just asked to show that the chain rule sort of survives when we expand our definition of the derivative to include our u dot grad term. And so how you would do a problem like this is just start from the definition, and then write out your definition. So if you have d by dt of f squared, you can just write out the definition, which has partial by partial t, u partial by partial x, v partial by partial y, w partial by partial z, and all of those are operating on f squared. And then you can use the normal rules of chain rule differentiation for each of these 4 terms. Each one of these derivatives pops out at 2f df dt, df dx, df dy, df dz. And then if you just factor out those 2 f's, I'm sort of skimming the algebra a little bit, but if you factor out those 2 f's, we get 2f outside of 4 terms. Those 4 terms, you can recognize it actually as df dt, the material derivative, and so you end up with exactly 2f times capital df dt, which is what we were looking for. So if you're asked to do something with the material derivative, it generally is going to be based on the definition. So, and once you write down that definition, you're back to normal differentiation, partial differentiation. So all the regular rules of calculus, chain rule, product rule, go through. And so there's plenty of properties. You can also show, for example, that the material derivative obeys the product rule. And so understanding how to mechanically work with the material derivative, that's worth knowing. And again, I'm not saying that you'll get any of these exact questions, but this is the level of difficulty, this is the kind of content. Okay. Second one is sketching. So this is another sketching example. So this is a little bit of a different flow. We've mostly been doing vortices, but this is a little bit of a different one. So just sketch and briefly describe the flow given by the velocity field in 2 dimensions. U of x equals x, and v of x equals y. So previously we had these flipped. It was like negative y and x, and that created a vortex. But this is going to be something different. So the x component is proportional to x, and the y component is proportional to y. So do the same stuff. What I did was I just decided to pick 4 points, and I picked these 4 points the sort of four cardinal directions, sort of east, north, west, and south. So I pick 1, 0, 0, 1, negative 1, 0, 0, negative 1. And let's just plug in those 4 points into our formula for our vectors. When we do that, we find that at x equals 1, y equals 0, we plug in our u as xy, so we get 1, 0, and I like to draw the arrow, so 1, 0 corresponds to the arrow to the right, and we go around the circle, where you find it goes right, up, left, down. And so what this flow looks like is this, and so it's sort of exploding outwards from the center. So this is called a diverging flow. We haven't actually talked about the divergence operator before. You may have seen it already in vector calculus. But that's not critical. The key thing is just the description, that this is somehow flowing outward from the center, and it's actually getting faster and faster as you get away from the center. So you wouldn't necessarily need to draw all these arrows, just the 4 arrows, the four cardinal directions would be fine. But the basic idea of being able to plot a few points and get a sense for what the flow looks like, that's important. Kinematic equation. So this one is about solving the kinematic equation in 1D. So there was a question, could you get it in 2D? You'll either get kinematic equation in 1 dimension or 2 dimensions, but the differential equation will be solvable in either case. This is a 1-dimensional example. So previously in class, we did u of x equals lambda x, which is a flow getting faster and faster as you go to the right. This one is similar, but a little bit different, x squared instead of x. And that changes the differential equation. So you're asked to solve the kinematic equation and describe the motion of the parcel. So the first thing to do is write down what the kinematic equation is. This is the general form that will be on the formula sheet. So in our 1D case, u is just ax squared, so we get axp squared here is equal to the derivative. And this is a separable equation. So you can divide by xp squared here, cross multiply by that dt, and you get this integral expression. 1 over x squared is the same as x to the negative 2. That can be integrated directly. So we get here 1 minus 1 over x, evaluated at the position and the initial condition, equals a times t. And you can rearrange this, and after a little bit of rearranging, we get this formula. The reason that's all circled and stuff is because I was emphasizing things as I was going. There's a video version of this. So we get this formula for the trajectory. Xp is an explicit function of x naught, which is the initial position, a, which is the constant from the equation, time, and x naught are again the initial position. And so this one is a bit tricky to analyze, so I wouldn't give you one that's quite this complicated, but it's an example that I just knew how to do offhand. It illustrates the idea. So in this case, what's happening is, as time runs forward, so when t is 0, that part is 0, so we just have xp equals x naught. And then as t starts increasing, we have 1 minus this. So this number is getting smaller because we're extracting, as t increases, we're subtracting a bigger and bigger number. This denominator gets smaller, and so the value gets higher. So as t increases, xp increases, which means that it's moving to the right. And some very interesting thing happens here. This bottom can actually be 0. It turns 0 when t is equal to 1 over a x naught. That's a bit of analysis that, again, I probably wouldn't give you something we had to do that on the test. It turns out, in this particular case, the particle actually reaches infinity in finite time. The x squared flow field is so aggressively accelerating that the particle runs all the way to infinity in finite time. Just go through the example, understand the mechanics. Don't worry too much about the mathematical subtleties of this particular example. But this kind of idea of you're given some one-dimensional flow, solve a separable equation, plug in your initial condition, write down the trajectory, that's something that you might be asked to do. And then some explanation questions. So you'll get some questions that are more conceptual explaining. And so here are just some random examples that are of the type you might get. So I did, for example, so naively, so explain the following. So naively, one might expect that the acceleration would just be the partial time derivative of the flow. So a would be equals question mark, meaning we're not sure if this is true or not, partial u partial t. So we know that's not the full formula. This is missing the u dot grad term. So explain in your own words why this is not the complete acceleration. It may be helpful to think of an example in which the time derivative is 0, but particles are still accelerating. And so for this case, you could give the example of the river that we talked about earlier. In this case, if you draw this diagram, the parcel floating down the center, it starts to accelerate, even though from a top-down perspective, the flow is not changing. The velocity at every point is staying the same, but the parcel's moving through spatial variability. And so as it gets closer to the waterfall, it speeds up. And so in this case, you can give an example that has this property. You wouldn't have to be as concrete as this, but the key thing is that spatial gradients here, apologies for the bad writing, can cause accelerations rather than an explicit change in time. So accelerations can come either from gradients in space, du dx, or explicit time dependence, du dt. So that's why that formula is incomplete. And then the last one is about pressure. And so I said here, without doing any calculations, state the net pressure force on a submerged cube, assuming that the pressure is uniform everywhere in the fluid, so that P is actually just equal to P naught is a constant, and explain your reasoning. And the idea here is that you have a cube, there's forces on all 6 sides, pressure forces, but those forces, the pressure force is equal to the pressure times the area. If the pressure is uniform everywhere, then every side feels the same force. So P times A on the 6 sides. And so overall there's a squeezing force, but because of the symmetry of the situation, there's forces on every side. Those forces balance each other exactly. And so the cube is squeezed, but the net force is 0. And so you might get a question, something like that, where I say, don't do any calculations. And if you're asked to not do any calculations, the answer's got to be 0 or 1 or something really easy like that. And just explain using physical reasoning, why does everything cancel, or why does it have to be at 0 or something. Okay, so if you want a more detailed explanation of those, you can check out the video on YouTube. Other than that, I would suggest to focus on the homeworks, the 2 homeworks, the questions that I emphasized, the in-class examples, and these practice problems. And then there's not going to be tricky proofs and derivations from the class that we didn't spend a lot of time on. That's about it. So try to show up on time so that you can have the full class period to do your test. Try to remember to bring a calculator. And if you have any questions before Thursday, feel free to let me know. I'll do my best to answer before that. Okay, thanks.